Welcome to Calculus. Today we will investigate solving related rates problems that have to do with squares and circles. We'll take a look at two examples, one of each. Our first example is about a hypothetical square that grows so that the length of its sides are increasing at a rate of 5 meters per minute. Question we want to answer is how fast is the area of the square increasing when the sides are 15 meters each? I want to start off this related rates problem by identifying the variables that are presented in the problem. So within a square, I can think the dimensions that we're measuring really are the side length. So I'm going to call that L. And another measurement that we're taking here is definitely the area. So that one we'll call A. Now, after I've identified the variables of the situation, the side length and the area of the square, I want to say what type of rates that I'm interested in within the scenario. So I see that I have this statement that the length of the sides are increasing at a rate of 5 meters per minute. So I can identify that as a rate that involves the side changing as time changes. I'm going to call that dl dt. And that is a constant value here. It's given as a rate of 5 meters per minute. Those sides are increasing at that constant rate. The other rate that I'm looking at is how fast is the area of the square increasing. So that one we don't know. And in fact, that's what we're going to try to solve for when we set this equation up and investigate how to come up with that rate of the area changing as time changes. I'm also given one detailed piece of information. I'm told that the length of the sides that I'm interested in is 15 meters each. So I should mark that as well. That's a specific length that's given within the scenario. And really it's at that instant that we want to come up with what is the rate of the area as it's growing. So once I have my variables, my rates, and any specific data kind of organized in this way, I want to come up with an equation that relates my two variables. In this case, I've got only two variables. So when I think about how the area of a square is related to the length of the sides, I have a formula that I can pull directly. It's the area equals the length squared. So for this situation, that formula really presents itself quite readily. Now, once I have that formula, in order to get this to a point where I can discuss rates, I want to take the derivative of both sides with respect to time. So I'm immediately going to take derivative of the area as well as the derivative of the length squared. And what that will give me is this related rates equation, dA dt. So on the left there, we don't have to do anything because it's really in a way an identity. It's like the y equals x. So its derivative is just 1, and I'll leave that differential. And then the derivative with respect to time of the length squared is going to be 2 times the length times the rate dl dt. Now that equation really is going to be our entry into answering this question: how fast is the area of the square increasing when the sides are 15 meters each? I just need to make some substitutions. I want to substitute for the specific length, the 15 meters. And I also see that I've got recorded up here that the rate that the length changes with respect to time is 5 meters per minute. So I'll make a substitution for dl dt as well. And the way that this equation is set up, I have dA dt, the rate of the area as time changes, equals this product, 2 times 15 times 5. And if we multiply that out, that's going to give us 150 square meters per minute. And that's complete. We can tell that it's complete in a number of ways. One of them is that the units are consistent. Meters squared per minute, that is a measurement of the area changing over time. So our units should corroborate what are we trying to find? What question are we trying to answer? So that's a scenario involving a growing square. Let's see an instance that involves a growing circle. So this example says that water is leaking onto a floor and forming a circular pool. The radius of the pool increases at a rate of 3 centimeters per minute. How fast is the area of the pool increasing when the radius is 3 centimeters? Let's start again by identifying our variables. So my variables for this question would definitely be, since I'm talking about a circle, the radius. And we'll call that R. And then like our last question, we're really kind of prompted into discussing the area of a circle. Now, again, I want to say what type of rates I'm interested in. So definitely I have given here that the radius of the pool increases at a rate of 3 centimeters per minute. So from what I'm seeing here in the scenario, that's dr dt, the change of the radius as time changes. And that is a constant given as 3 centimeters per minute. So I'll notate that. The question is asking how fast is the area of the pool increasing, and what that implies is I'm looking for the value of dA dt, the change of the area as time changes. So as I set up an equation and take the derivative, I'm looking for dA dt. And lastly, I have this detail information that the radius equals 3 centimeters at the instant when we are looking for that dA dt, the change of the area. Again, once I get the variables, the rates, and the detail data recorded and organized, then I need to try to relate my variables in an equation. And like our previous view on a square, where I related area and length, here I can relate for this circle area and radius. So recall from geometry that the area of a circle equals pi times the radius squared. And that'll work for us. So I've got my equation, and I'm going to jump right into taking the derivative of both sides. So I'm going to take derivative of a, and that's going to give me really the same as we saw with the square dA dt. We can think that the derivative of a is 1. I'm also going to take derivative of the right side, so the derivative with respect to time of pi r squared. So that's going to be 2 from the exponent on the radius. Pi would just remain, that's a constant coefficient, times the radius, and then the power would now be 1 times the change of the rate over the change in time, dr dt. Once I've got that equation differentiated, I want to make my substitution. So I see again that the rate that I'm trying to solve for is dA dt, and this equation is solved for that rate. So I just need to substitute in for my variables on the right side. So I've got 2 pi, that I'm just going to leave as is, times the radius. So again, we're interested in specifically the radius at 3 centimeters. And that's times the dr dt value, which also is 3, but with the units centimeters per minute. And then once I make my substitutions, I want to simplify the product. So that's 2 times 3 times 3, that's 18. And I'll just leave pi as is. My units here, centimeters times centimeters, will be square centimeters per minute. So again, if I check my units, That's consistent with the rate I'm solving for. The change of area with respect to time matches my square centimeters per minute. Thanks for joining for this investigation of square and circle related rates. See you soon.